Good morning to all. Let us start the laws of motion, the lecture 2. Today I am going to cover the following topics: Newton's second law of motion, important points about second law, impulse. So let us discuss Newton's second law of motion. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force takes. This you have already studied in class 9th. So force is proportional to change in momentum upon time taken. If force F changes the velocity of a body of mass m from v to v plus del v, then its initial momentum p is equal to mv will change by p del p is equal to m del v. According to Newton's second law, F is proportional to del P upon del T, or F is equal to K del P upon del T, where K is a constant of proportionality, or F is equal to K limit del T tends to 0 del P upon del T. This is the instantaneous value of the force. Or we can say that F is equal to K dP upon dt. So limit del T tends to 0 del P upon del T. This you have studied in previous lesson. So this changes to dP upon dt in the differentiation. So from here we can say that F is equal to K d by dt mv. Or since in the differentiation of mv, m is constant and constant term can be taken out from the differentiation. So it reduces to F is equal to K m dv by dt. And we know that dv by dt is acceleration. So in place of dv by dt we can write A, and it reduces F is equal to K ma. So we can say that if force of 1 Newton applied on a body of mass 1 kg produces an acceleration of 1 meter per second square on the body, then 1 is equal to K into 1 into 1. So here we have taken F is equal to 1 Newton, mass is equal to 1 kg, acceleration is equal to 1 meter per second square. Then if we put it in the equation, we get F is equal to, we get K is equal to 1, and then we can say that F is equal to ma, and force is equal to mass into acceleration. So we can say that 1 Newton is that force which produces an acceleration of 1 meter per second square on the body of mass 1 kg. So in this way we can define 1 Newton force. Now acceleration A is equal to F upon m. The acceleration produced in a body is directly proportional to the force acting on it and inversely proportional to the mass of the body. As we have derived in the previous slide, the F is equal to m into A. So from here A is equal to F upon m. So we can say that acceleration produced in a body is directly proportional to the force acting on it and inversely proportional to the mass of the body. So force is a vector quantity. Force can cause acceleration or deceleration. For example, accelerator of a car accelerate it and brakes decelerate it. SI unit of force is Newton. 1 Newton is defined as that force which, when acting on a body of mass 1 kg, produces an acceleration of 1 meter per second square in it. Place an 100 gram on your outstretched palm. The force you feel is nearly 1 Newton. So if you place 100 gram mass on your outstretched palm, the force you feel will be equal to 1 Newton. Now some important points about second law. In the second law, F is equal to 0 implies A is equal to 0. This is obviously consistent with the first law. First law says that if no force is applied on any object, then acceleration will remain 0. Means the body, if it is in rest, will remain in rest. If it is in motion, it will continue to be in motion. So from the second law, F is equal to ma. If F is equal to 0, it implies A is equal to 0, which is our first law of motion. The second law is a vector law. It is equivalent to three equations, one for each component of the vector. Now since F is a vector quantity and vector quantity can have the components along x-axis, y-axis and z-axis. So from the equation F is equal to ma, we can have the three components. Fx del p dpx upon dt is equal to max, fy dpy upon dt is equal to may, Fz is equal to dpz upon dt is equal to maz. This means that if a force is not parallel to the velocity of the body but makes some angle with it, it changes only the component of velocity along the direction of force. So if the force is not acting in the direction along the direction of the velocity, then it will have the components, and the x component will change only the component of velocity along the direction of the force. And also one conclusion comes, the component of the velocity normal to the force remains unchanged. For example, in the motion of projectile under the vertical gravitational force, the horizontal component of velocity remains unchanged. This you have studied in the previous lesson, that the vertical component, since gravitational force is acting in the downward direction only, and in that case the horizontal component of the velocity throughout the motion is not affected by the acceleration due to gravity. So ux is equal to u cos theta remains unchanged during the complete motion. The equation F is equal to dp upon dt is equal to ma is applicable to a single point particle. However, it is same for a rigid body or even more generally to a system of particles. In this case, m refers to the mass of the rigid body or total mass of the system of the particles, and a refers to the acceleration of the center of mass of the system. Any internal force in the system are not to be included in F. So it is a F is equal to dp by dt means is applicable to a single point particle. The whole rigid body is supposed to be a single point particle. The second law is a local relation. Now local relation, which means that force F at a point in space at a certain instant of time is related to A at that point at that instant. Acceleration here and now is determined by the force here and now, not by any history of the motion of the particle. Now for an example, suppose any person is traveling in a train or in a bus and he has an object, or for an example say he has a ball in his hand. If he throws the ball out from the window, then as the ball comes out from the window, then it will not have any relation from its history, means whatever the acceleration is acting when it is in the car will not be taken into consideration as soon as it comes out from the car. When it is in the space, then it will have only the acceleration due to gravity. So force is, second law is a local relation. Impulse. When a ball hits a wall and bounces back, the force on the ball by the wall acts for a very short time when the two are in contact, yet the force is large enough to reverse the momentum of the ball. In this situation, it is difficult to ascertain the force and time duration separately. However, the product of force and time, which is the change in momentum, is a measurable quantity. This product is called the impulse. So let us understand it again. When you throw a ball to a wall, then it comes back, and the time of contact of ball with the wall is very short. So here the time and force to ascertain the force and the time duration separately is not possible. So in that case, the product of force and time, which is equal to change in momentum, is a measurable quantity. So we give a name to this measurable quantity, impulse. So impulse is equal to force into time duration, and time this is equal to change in momentum. Impulse is represented by letter J, so J is equal to F into T. A large force acting for a short time to produce change in momentum is called impulsive force. So impulse is force into time duration, but impulsive force, we can say that when the large amount of force is acting for a short time to produce change in momentum is called impulsive force. There are many huge importance of the impulse in practice. A high jumping or a long jumping athlete is provided either a cushion or a heap of sand on the ground to fall upon. This you must have also noticed that when you are doing a high jump or a long jump, then you need a cushion or a heap of sand just to provide you to protect you not to be hurt. Why it is so? The cushion or a sand helps to increase the time in which the momentum comes to zero. This decreases the rate of change of momentum and hence the force, so the athlete does not get hurt. So the So the cushion or a sand helps to increase the time in which the momentum comes to zero. This decreases the rate of change of momentum and hence the force. So the athlete does not get hurt. Packing material like thermocol, corrugated sheets, bubbled plastic sheets, straw, paper, strands, etc. are used while packing glassware, chinaware, electronic devices, etc. These materials help to increase the time in which the momentum comes to zero when jolting and jerking takes place. This decreases the rate of change of momentum and hence the force, so the athlete do not get broken. So the articles do not get broken, because you know that J is equal to F into T is equal to change in momentum. So if the impulsive force is acting for a short time here, if the time duration is increased, because change in momentum is constant, if time duration is increased, then F will decrease. So in that case, here we are increasing the time duration, and as a result the impulsive force or the F is decreasing, so that the article is not get broken, or the athlete who is running, who is doing high jumping, will not get hurt. Similarly, the shock absorber are provided in a vehicle to allow more time during the bumps and jerks. A seasoned cricket player stops the ball by drawing his hands along the direction of motion of the ball, thus by allowing more time and to apply less force. Now this is the ball. The cricketer, he draws his hands, or in doing this he increases the time duration, so the impulse or the impulsive force reduces. A fast moving cricket ball has a large momentum. In stopping the cricket ball, its momentum has to be reduced to zero. When a player moves his hands back, the time taken to stop the ball increases and hence the rate of change of momentum decreases. That is, the force exerted by the ball on the hand decreases, so the hands of the player do not get hurt. So that is all for today's lecture. Thank you.